Good morning, class. Today is actually Sunday, November the 8th. I have to do the video a day early. And this is then the video for November 10th lecture. And I have things already written on the board because I want to use the screen today. And so I want to avoid the defocusing issues when I stand at the board. So apologize for that. And, here I am. And we'll just do it this way. And today should be a relatively short lecture because we're just going to finish up a little thing on ion implantation that you need to understand, and then talk just briefly about chemical mechanical polishing. And you can see I have a few notes I already put on the board so that I don't have to stand up and worry about focusing. So let's see if actually I can make the this a little bit bigger. Okay, and I wanted to start out by sort of I found this nice article on the web. I can give people the link if they're interested, but I thought it was nice because it has a nice set of slides here that sort of pictorially show you kind of what's happening in the implantation process and annealing step afterwards. And starting with this slide, okay, in the implantation process, before implantation, of course, you have a nice crystal, which usually is silicon atoms there. And then after implantation, the crystal is essentially damaged. I mean, not to the extent I believe that it's shown here, but I mean, what he's saying there is roughly true. The area of the implant kind of loses all its crystallinity and becomes amorphous. And so you have to fix that. And the article here has a nice set of slides. So that's before implantation, nice crystal. After implantation, it gets all messed up, which is amorphous. And then you perform the annealing. And I thought it was just a nice set of slides here because, okay, so here's your implantation. The solid atoms there are what you implanted, which, you know, as he has written here, may typically be a dopant atom. And what he's showing there is that the implantation damage only extends down a certain distance. And so if you if I can use the cursor here, see where my cursor is. So that's supposed to indicate that the damage has gone down a certain depth, approximately the same depth as the implanted atoms themselves. And then you finally reach where the crystal is not damaged. And so the crystal is on an ordered array. And so what's happening here in the annealing step is somewhat similar to epitaxy, in the sense that you have this fairly amorphous implant damaged region of the crystal above an essentially perfect version of the crystal. And so as you anneal, now what's going to happen is that starting at the bottom there, see, those atoms are going to go into the right position as you're doing the annealing. And as you can see here, what he's shown is that as those atoms, those original atoms are hitting and getting on the right lattice position, so are what you implanted, you see there. And so you're getting your dopant on the lattice site. And so as you continue to progress, then you extend the crystal upward still, and also the dopant atoms go on the lattice sites, and you just keep going like that, and then eventually you reach the surface where basically everything is now an ordered crystal. And I'm not sure if he has another slide here. Basically showing it, continuing to go there. The crystalline, the fixed or annealed crystalline region continues to go up there and get fixed, and then finally, I think he has the final slide there. Finally, after annealing for a proper amount of time, the crystal is all fixed and the dopant atoms are on the site. So I just thought that was a nice set of slides that 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 show, you know, how this all works and how the annealing process fixes things, and also at the same time results in these dopant, the implanted dopant atoms going on the crystal sites, where of course they have to be in order to act as dopant. Okay, so so there's that, and also I wanted to discuss one final thing, and I have to correct the syllabus to include a section of the textbook, because where is it here? I think I passed it. Yes. There's one thing that we need to cover, and I made up a homework problem on this that I hope you'll find is interesting, which is, you know, basically there's something called the channeling effect, which sort of makes sense if you think about it, that if you are going to implant the ions, and here we're showing an ion getting implanted, that since you're implanting them into a crystal, you can have the unfortunate incident that the ion, you know, sort of travels, you know, perfectly, you know, in between the lattice planes, and so it goes way down low into the wafer, and that's highly undesirable, because what happens then is you sort of have kind of a mirage region of dopant atoms that are channeled far below where you actually want them to occur. I mean, you know, as shown in the previous slides, you want everything to be happening near the surface, and so you have a well-controlled region of implanted ions. Whereas if you have this channeling effect, there's going to be some that are going to go way far down, and you'll have sort of the region you expected up here, and then sort of this odd distribution of implant ions down there. So what he's showing here is and I'll say one technique for correcting this problem, which is you just simply sent the ions in at an angle. And so the idea there is that since the ions are coming, the beam is coming at an angle, it's more likely that it's going to hit one of the atoms before it sort of channels. Now you can sort of get the idea of what's going on here in the sense that if you treat this drawing as sort of actually representative of the geometry of the system and the atoms, that if the angle is very shallow, what's going to happen is that the atom is just going to sort of bounce off of one of the lattice atoms and keep going, and it will still channel below a certain angle. And the point is that you want a certain amount of energy transfer to occur in that first collision and subsequent collisions so that the implant atom stops. And so the way to understand this is that if this angle is too shallow, all right, you will still channel essentially, you know, just sort of like balls bouncing here. If the ball doesn't lose any energy in the collisions, it's just going to keep going. And so you want this angle high enough that it hits that atom and gives some of its energy, or a good fraction of its energy, to the latticed atom. And as he says in the textbook, that angle is typically 7 degrees. And I sort of tried to look up, you know, why 7 degrees. The reason appears to be that, well, that's as far as they can tilt most implanters. You know, the kind of thing is that I don't think they've determined an optimum angle for this. You know, sort of, you get the idea that if the angle is too big, and he has a nice drawing in the notes that maybe I'll show in a little bit, that you don't want this angle too big, because then you lose your pattern, in the sense that because you overshoot your pattern and you implant in a region where you're not supposed to. Maybe I'll show a drawing from the textbook in a little bit on that. But so 7 degrees is the typical angle for a variety of reasons which are not perfectly well understood. Now, in the notes, he shows, and maybe we can go to the notes now. So let's go up here. All right, so here he's showing the effect of tilting too much, which is, say you're making a MOSFET now, and this is a planar MOSFET. What's going to happen is, because of the topography of your gate there, that in fact your doped region will go off to the side too much because of a shadow there. And so for that reason, you don't want the angle too much. And so again, for kind of this reason, as well as the fact that most implanters only can go to 7 degrees, that's the typical angle. Now here on this figure here, there's another technique, and that's what that's what I showed here on the board up there, that is used for this problem, which is that instead of just implanting directly on, well, no, it's not shown in that figure. Maybe he does not have a figure. Okay. Let me see if I can find it here. Okay. All right. Well, I'll have to refer to the drawing on the board then. I thought there was a figure here where we showed. I know he discusses it in here, and I will alter the syllabus to include that section. That if because of this shadowing effect, it is determined to be undesirable to tilt the implanter to avoid the channeling issue. You can see what I have at the top there shows another technique of dealing with this, which is that you deposit a thin silicon dioxide layer, or deposit or oxidize that layer, and what that's, I mean, the way to think about that is it's similar to ground glass and light. I mean, if you've ever seen frosted glass, you know that if you try to shine light through it, it gets scattered in all directions. And sort of the same thing happens here. If you have a fairly thin oxide, thin enough so that the ions can get through, but thick enough that it does what I'm showing there, which is that going through the oxide, the ions the direction of the ions is sort of scattered, so that they're not all coming straight down. That's another way of dealing with this issue. And honestly, I was trying to look up, and I think this is one of the areas where I couldn't find, for example, for a real foundry like Intel, what technique they use. And probably it's sort of kind of a secret. But those are the two techniques, and I thought it was shown here, but I was wrong. You either, as shown here, tilt the implanter to avoid this channeling effect, or as I have shown on the board there, you put a thin oxide that acts to scatter the ions. Okay, and that's all I was going to do on ion implantation, and so I wanted to fill in that issue on channeling. And again, I will alter the syllabus so that you know that that's included. All right, now we're just going to cover chemical mechanical polishing a little bit. And in chemical mechanical polishing, all right, you have a you have a tool like this. This is showing it sort of in schematic. It's a fairly large mechanical instrument that has a platen that has a slurry. First there's a pad here, and then there's a slurry. Okay, I'll talk a little bit about that in a second. A slurry is basically kind of a liquid with some very fine abrasive in it, for example. And you can have slurries with abrasive sizes all the way from 10 microns So if you had a slurry with 10 micron particles in it, uh, it would, you know, really grind it. Then it's more grinding than polishing. Um, and you can go to slurries all the way down to, you know, tens of nanometers size particles, nanoparticles, in which case it's actually polishing. Now that's more mechanical polishing. We'll talk about chemical in a second. Um, okay, and so the wafer is held upside down on this chuck here. It's a vacuum chuck basically holding the wafer. And what's very important in this machine is that this is rotating at the same time as this is rotating. It's called a planetary rotation arrangement. And so as this is rotating and then this is rotating, you have sort of a natural kind of like uniformization of the force on the wafer. And so you get a very uniform reduction in thickness as you're performing the polishing. And now, as part of my career, I've done certain polishing for different reasons than usual. And what I can tell you is that if you're using a slurry, it's basically rate versus finish, in the sense that if you use larger slurry particles, you'll go faster, and again, that's sort of more like grinding. Whereas if you go to finer slurries with smaller particles, your rate of removal of material will go much slower, but you'll get a nice finer finish. And so a typical thing to do is if you want to reduce the thickness of a relatively large amount of material, is that you'll start with a slurry that has fairly large grit, and you'll do that in a grinding step to remove however much material you want to do, and then you'll change the slurry to one with a finer grit to produce a polish. Now the main reason for chemical mechanical polishing, we haven't talked about the chemical yet, is in the IC industry, is polishing of deposited films, which basically means what is shown in this drawing here, which is, let's say you want to produce a metal interconnect. What happens is that you have certain features. Okay, so this is showing okay, so the idea here, this is not a very good drawing. Basically, when you deposit metal layers on an integrated circuit, let's just forget about what's written here, and let's focus on what's on the left here, which is, let's say you want to deposit a metal interconnect, and let's say it's these two places here. No, actually, let's use the one on the right. Okay, so because that's sort of easier to think about. Okay, imagine you have an oxide opening here, all right, and you want to deposit a metal interconnect in this region here. And so what you do is you deposit metal, and it sort of goes down in the hole as well as all over. Now I've taught you sort of about liftoff, which is a very sort of coarse research grade process for defining metal context. In the real IC industry, what you do is you deposit your metal, it goes in the opening, it also goes where you don't want it, and then you polish down so that you leave a pristine surface there with your metal interconnect line there. And it's really actually extraordinarily amazing, because this process is done in today's ICs. I mean, you can have upwards of 50 interconnect levels. That is, so you have an interconnect level here, and then you deposit oxide on top of that, and then maybe you make an opening over here to deposit an interconnect level over there, and you perform this step of making an depositing an oxide, making an opening, then depositing metal, then polishing it back, then depositing oxide and making an opening, etc., 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 like 50 times. And it's really astonishing that over a 12-inch wafer, they can achieve planarization, polishing and planarization down to what is essentially on the order of a 10 nanometer level, and do this, dozens of times to get a integrated circuit on a chip. I can tell you that this polishing aspect of integrated circuit chips is one of the major accomplishments of the last 30 years that has allowed, it's not just making the transistors smaller. If you think about it, the more transistors you put on a chip, the more interconnect lines you have to connect them, and so the more interconnect levels you have to have, and so this polishing mechanism is not just a minor contribution to the IC industry. It's actually key. All right, so that's the main use is as I have listen here, polishing and deposited films, particularly metal films, in order to perform this step of defining a layer. And I think that was the main thing I wanted you to get there. And as we've been going through this, like for polishing here, there's various equations and things like that, various information here, and I prefer to just sort of tell you qualitatively what I want you to remember, and then go from there. Now, where I view so far actually we haven't talked about chemicals, and what he says here, and right, there's a reason why it's called chemical mechanical polishing. So far all we've kind of indicated is mechanical force involved, that basically there's a slurry, you're pushing down against it and you're rotating, and so you're removing material through a mechanical interaction of the slurry and the wafer. You can add chemicals to the slurry such that at the same time you're mechanically removing atoms from the wafer, you also have a chemical reaction taking place that's removing atoms from the wafer. And there I have, the only thing I can tell you is that I've used gallium arsenide a lot in my career, and so for gallium arsenide, what I have written on the board here is that you do actually straight chemical polishing. There's no mechanical. It's not a slurry in the sense. It's just a chemical liquid, and it's bromine mixed with methanol. So if you ever have to work with gallium arsenide, or that works for some other 3,5 materials as well, you would use a mixture of bromine and methanol, and that would be your chemical polish. And I actually don't know or am not familiar with slurries which are both a combination of grits as well as a chemical that causes a chemical reaction. I have never used any slurry like that. The only slurries I've used are either purely chemical, like bromine methanol for gallium arsenide, or purely mechanical, meaning having a grit that causes the removal. But I haven't done one that has both. And now that's sort of it. That's the extent of today's lecture, and so that completes us up to chemical mechanical polishing. And again, I'll update the syllabus on the ion implantation to make sure you understand and are aware of the issue on channeling. Okay, and so that's it for today. Now, going forward, we're going to next cover bonding in the next lecture, and so I'll talk about what that means and the various types of bonding operations that you perform and why you do it. And then what we're going to do is we're going to start talking about specific recipes. Okay, so that's it for today. Talk to you on Tuesday.